Hello, everyone, and welcome to another episode of Solving Advent of Code in Rust and Trying to Learn Rust. I'm Eugene, and we also have. Sorry, get
Luciano.
right. Welcome. Thank you, everybody, for following along. If you've never done Advent of Code before, it's basically a coding challenge that is published every year in December, just before Christmas. And there's basically one challenge every day up until Christmas. We're working on last year's one. There's 24 challenges. You can find them on adventofcode.com. We should have a banner. There we go. Thank you. We work on this and publish all our code on GitHub. So you can go there if you want to see any of the previous stuff. We also have a YouTube channel where you can see our previous streams as well. So there's a link to the YouTube channel in the description of Twitch. If you're watching this on YouTube, there's a link to Twitch in the description of YouTube. So, you can find us from both places. Today, we're going to take a look at exercise 5 of the 2021 Advent of Code, and Luciano's going to drive.
Yeah, this is, by the way, something we have already solved. We have a PR to our repository. So today is going to be, rather than live coding it's going to be more of a walkthrough. And maybe we get some ideas on things we can improve. So we'll try maybe to play around with our solution. So let me share my screen and then we can discuss the current exercise. So let me pull up the README. Hopefully this is readable enough. So basically what we have to do, we are continuing our adventure game where basically we are in a submarine and we need to do a bunch of things to kind of survive and keep going with this submarine. And in today's challenge, basically what we have to do is there are fields of hydrothermal vents, whatever those are, and we need to basically figure out how to avoid them. So we need to program our submarine to figure out where those vents are and how we can go through them in a safe way. Now, the submarine is giving us some information, which is our puzzle input, and it looks like this. And you can imagine that these hydrothermal vents, they are like lines in a two-dimensional space. And more than lines, I would say they are segments. And so every line of our input is representing this segment. And you have a starting point and an end point. So this is the first point of the segment, and this is the last point of the segment.
Worth mentioning X and Y for a point.
Exactly.
Seems obvious, but just good to, yeah.
So this is pretty much X1 and Y1, X2 and Y2 for every single segment. The other interesting thing, which is specified here, is that those segments are inclusive. So the boundary points are included. So 0, 9 is part of the segment and 5, 9 is part of the segment. And the other thing is that we can plot all this input in a two-dimensional space. And if we plot this way, where basically we are counting every time a point is crossing a particular point in the space, we can see that, for instance, there are places where the lines intersect each other. The segments are intersecting each other. So for this reason here, we have a 2, because that means that this line and this line are intersecting here. So this point is pretty much being drawn twice. And similarly, this happens here. We actually have a segment in our input that is literally 1 pixel wide and overlaps here. And here as well, there is a little bit of overlapping. So this is just one way to visualize our input. But the idea, the task for this particular day, is that we should try to avoid to cross all the points where the counter is 2 or higher, because these are to be considered the most dangerous point for our submarine. So the question is, if we process all our input and we count for every single point in the bidimensional space how many times things overlap, like what is the count of the overlapping points? There is a caveat here that we need to consider only the lines here, only horizontal and vertical lines. And in our input, this is not a guarantee. We might have lines that are actually diagonal, so we should skip them for part 1.
Mm-hmm.
I hope that all of that is clear. Feel free to ask question in the chat if it's not.
It made sense so far, I'd say.
Okay, so let me try to show the input first. You can see that, of course, compared to our example, we have much bigger input and also much bigger numbers. But it's pretty much the same format. It's just a lot more segments. I think it's like 500 segments. So let's look at the solution. So the first thing that we do is, of course, defining a bunch of structs. So we define a point, which is effectively just x and y. But notice that we make this point comparable pretty much. And this is something we are going to need later. So this is where we derive all these traits. Then we also define a segment, which is just a combination of 2 points, point 1 and point 2. And segment, it's something that has a couple of helper methods. The first one is straight, which basically can tell us whether the segment is either horizontal or vertical. And this is something we can use to filter out our input. And then we have another helper method, which is called walk, which gives us a segment walker. Now, this is something we invented, but it's nothing else than just an iterator that allows you to go from the first point in the segment to the last point, and at every iteration you are getting one of the points in sequence. So if you have, I don't know, an horizontal line that goes from 1, 0 to 3, 0, you will get 1, 0, 2, 0, 3, 0, and then the iteration completes. So let's see how all of that is implemented, because this is probably the most interesting part of the solution. Actually, before that, we, of course, have a parsing method. So our input is just a sequence of segments. So it did make sense to have a from string where if we take a line of that input, we should be able to get a segment. And this is actually pretty simple because we split once on the arrow, and then we split the two sides on the comma, and we get the 4 numbers. And with the 4 numbers, we can create 2 points. And with the 2 points, we can create a segment. So
just a thought, it might be worth showing on the iterator part of the segment walker. Before we go into how it works, it might be worth showing how we're using it, because I think that would clarify the context for why it's built the way it is.
That's actually a very good point. So let me go down to the actual solution. Just keep in mind that we also have a space struct, which is like a bidimensional space. So it's literally a collection of points, but we represented that using a B3 because we don't really know how big is the space. We only know where the lines are, the segments are. So what we are doing is every time we find a new point in a segment, we are just allocating that in a B3. And if it was already there, we just increment the counter. So it's literally like an hash map where for every point, we are going to increase the counter. And we can assume that if it's 0, if you take any random point, if it's not in the B3, that means that it was 0. Like we never draw a line over that particular point.
Yeah.
Also keep in mind, this is actually where we use that walk. So I'm going to mention this one. So given a space, we have an helper function that is draw segment, where you can pass a reference to a segment, and it's going to be able to draw all the points in that segment inside the space. And what it's doing is literally taking the given segment, is using walk, which is going to give it an iterator over every single point of that segment. And then for every single point, we literally do basically an insert where we say, give me the point or a default, like create a new point, and then increase the counter by 1. So this is a pattern that we have seen before where we can literally do like a default dictionary in Python if you want. So you can say, give me the current value, or if there isn't one, create a standard one, and then you can use a reference to change the value and increase it by 1.
Makes sense.
And because this is a usides, or default will give us a 0 usides, so that will work it will always increase it either from 0 to 1 or from the current value to +1. And with that, our solution becomes pretty simple, because what we do is we take the input, we take all the lines, we map our parse function. So we get, for every line, we get a segment. We can unwrap because we trust that our input is well formatted. So we are not really handling error in the best way, because we are assuming we know that the input is fine.
Mm-hmm.
Finally, we use filter using that function segment is straight, which allows us to skip all the lines, all the segments that are not straight, which is what is requested for part 1. At this point, this is just an iterator. So at this point, we are not even consuming it. We are not reading the data. It's just defining the structure of how we are going to read the data. Then we can create a space using space default, which is just going to give us an empty B3. And finally, what we do for every segment in this iterator, so at this point, we really start to consume the input. What we do is we call draw segment. At that point in our space, we have a sparse matrix of points. And what we need to do is literally just filter for the ones that have a value bigger than 1, which means points that we have been drawing more than once, and we just count. And that's pretty much it. Does that make sense?
It's clear enough to me, but yeah, people in the chat should let us know.
Let me.
We should go through the segment walker now, I think, right?
Yeah.
Because that's the
Let me run the test
interesting
actually for part 1, just to make sure that all of that works. Seems to be working. Now let's discuss the walker, which is probably what was the most complicated part, in my opinion, of this particular exercise. So as we said, segment walker is nothing else than an iterator that knows how to go from a starting point to a destination point. And for this reason, it needs to keep state, because it needs to figure out where it's starting from, where it needs to finish, and at every iteration, what is the increment in the direction X and Y. And it also needs to know, of course, what is the current point in this segment. We also have a completed, and we'll see why, because it's kind of convenient to have and avoid to, well, and figure out when we already reached the last point, so we don't need to, we can return none in the iteration and complete the iteration effectively. So, of course, we need to have an helper constructor, because we only want to give it a segment, and it needs to calculate all the initial state. So this is the function that will do that. So we can easily initialize a segment walker from a reference to a segment. So what do we do? The first part is actually very easy. We just take x1, y1, x2, and y2 from the 2 points, starting point and destination point, so p1 and p2. Then this is actually interesting. This is something that I haven't used often yet, but in Rust you can use this compare function, which allows you, in this case, we're comparing numbers, but you can use this for every comparable type. And we are saying, we are trying to determine what is the increment in the x-axis. So we have 2 points. They might be at the same level. They might be at different levels. So we're trying to figure out how to move step by step so that we can get from point 1 to point 2 on the x-axis. So what we do, we actually compare the final point, the coordinate x of the final point, and the coordinate x of the first point. And this is going to give us 3 possible results. Either the last point is greater than the first one, either is smaller than the first one, or they are equal. So if it's greater, that means that from x1 to get to x2, every time we iterate, we need to increment x by 1. If it's smaller, that means we need to decrease x by 1. And if they are the same, it means you are walking on a straight line. So pretty much, sorry, you are walking on a vertical line. So x never increases because it's always the same point.
Yeah.
Similar stuff we do for y. And yeah, it's literally the same. We are just comparing y2 and y1. And then we have current x and current y. Initially, we are starting from point 1. And at that point, we have everything we need to initialize the state of our iterator. X2, Y2, increment X, increment Y, current X, and current Y, and completed initial is going to be false, of course, because we haven't started the iteration yet. Keep in mind that we are storing X2 and Y2 just because we use them to know when the iteration is completed. We are not even storing a reference to the segment anymore. So we are not holding the segment. We are just releasing it at that point because we don't need it. We have everything we need in the state.
We also have a suggestion. We can put it in a single match.
We can put it in a single match. Both of them? Oh, yeah. I suppose we can compare tuples.
And we can keep a tuple of incrementer X, incrementer Y. Yeah, that's fair enough. Is there any gain to be had other than less code, I wonder?
I don't know. We can try that later. It's an interesting suggestion. I'm not really sure how to do it now, but I would like to try. So that's a good suggestion. Thank you for that. Let's keep it in mind for later. Okay, so
once we're done explaining, we could refactor, yeah.
This is just the initial state. So you give it a segment, it creates the initial state of the iterator. Now, how do we actually step through all the different points? So this is the logic. We need to implement the iterator trait. We have done this before, but pretty much what it does is allows you to do a for loop over an arbitrary struct. And this defines the behavior of what happens at every iteration. The cool thing is that you have this associated type. So you can say every time you iterate over this particular type of struct, you need to return this particular type of struct. So a segment walker will return points when we do a for loop over it.
Yeah. So we can mark them in our 2D space.
Exactly. So what do? We need to implement this next method, and this next method takes a reference, a mutable reference to the current structure, and it returns an option with the item. So this will return either some point or none. When it returns none, it means that we completed the iteration, and you should stop. If you're calling next manually, you can stop, or if you're doing a for loop, the for loop will be interrupted. Okay, so the first thing that we do is kind of a base case. If we are in the completed state, we just return none because it means we reach the last point. There is nothing else we should be doing, or no new point that we can discover. Otherwise, we can calculate the next point. Actually, we already calculated the next point in the previous iteration. So we just build the point using current X and current Y. So if this is the very first iteration, current X and current Y will be the first point in that original segment. Now the next thing that we should do is by the way, this is the point that we are going to return at the end. But before returning it, we want to update the state so that at the next iteration, we know what's the next point. So we do that a little bit eagerly, like we always pre-calculate the next point. Maybe we could do this differently, but this implementation works.
Mm-hmm.
So what we do here, we are basically checking if the point we just prepared to return is the last one, then we need to set completed to true. So the next time we go here, we're going to return none. Otherwise, we need to calculate the next point. Calculating the next point is actually very simple because it's just taking the current X and adding increment X, current Y and adding increment Y. And then we return.
Simple enough.
I don't know if there are any questions on that. I think we explained pretty much everything else.
Yeah, that's pretty much it for part 1. We ran the test earlier, so that works. I don't know if it's worth going through that again.
We do have some tests here of the walk line, just maybe to clarify a little bit more how this works. But basically here, if you give it the first point x0, y0, and the last point x2, y2, when we walk through it, and here we're doing segment walk collect, we expect that we'll be able to create a vector of 0, 0, 1, 1, 2, 2. So you can see how this approach is able to walk also not just horizontal or vertical, but also 45 degree.
Yeah.
It's not super generic, because of course if you have lines that are like diagonal but not 45 degrees, that approach doesn't work anymore. It's a little bit naive, but for the goal of this exercise, it was good enough.
Even curved lines wouldn't work. We have a comment which says, I'm not sure if maybe it's more of a question, but it goes, so there's no position structure. I'm not sure what you mean by that. We do have that space thing,
Yeah,
which is where we
maybe you
keep track.
missed that part.
Yeah,
So
maybe you joined later.
it's here, space B3.
It's basically, yeah, we're using the point as the key and then a number as the value. The number being 1 if there's a single line, or 2 or 3, 4, 5, depending how many lines intersect on that particular point. And the reason we did this is because the ask for the exercises is to calculate, to sum up basically the number of points which intersect in more than one, which intersect more than one line.
So pretty much if we were to draw all the segments and count how many times you are repeating a pixel, let's say, you could see something like this. And at the end, we need to return how many points or how many pixels, if you want, have a number that is bigger than 1. So 2 or more.
Yeah. I hope that kind of clarifies it. Hopefully. You'll let us know in the comments if not.
So should we move to part 2?
Yeah, we should.
So part 2, I think it was not very different from part 1. That was saying, considering only horizontal and vertical lines doesn't give you the full picture. You need to also consider diagonal lines. But the lines are exactly 45 degrees. So either they are horizontal, vertical, or 45 degrees. So if you, for instance, add these additional points, you will get something like this. So now you can see that there are lines going diagonally. So the ask is the same. Now you don't have to filter anymore. You just take the entire input, take into account that the lines can be diagonal, but only 45 degrees. So how many points do you get that there is at least a 2? So there is an overlap there.
Thankfully. Go ahead, sorry.
No, I was saying that the funny thing is that, yeah, because we already did this exercise, we implemented the iterator in such a way that it covers this case as well.
That's what I was going to say. Locally, our segment walker increments both x and y if necessary, so it can deal with 45 degrees.
Pretty much. So these two solutions are actually pretty much the same. The only difference is this line. Maybe actually another opportunity for removing some duplication here. But other than that, this should work because it's the same business logic. We are just removing the filter for diagonal lines.
What's interesting to mention here, and this is, let's say, yeah, it's somewhat related. We currently support horizontal, vertical, and diagonal lines, basically. But this solution would be absolutely unusable. I'm thinking about this from a game engine perspective. For instance, let's say you're building a 2D game and you want to store, positions of things and like direction of travel maybe for objects. And then we'd need to get this to be a bit more complicated. And I think it would need to calculate the incrementers on every frame, or, well, not every frame, but every time we're called in order to regenerate a board of positions. Then we'd have to deal with like an angle and calculate, angle, velocity, and then calculate incrementers. Just thought it's worth mentioning in case anyone has any interest in game design and is thinking of using this. Don't.
Yeah, this is intentionally done because of course it's not capable of drawing. We have that draw segment function, which is very limited. It's going to be able to draw only using that iterator, and that iterator is limited in the sense that knows how to iterate only horizontal, vertical, or 45 degrees. It's not going to give you any accurate result if you have different types of segments.
And it's only going in one direction as well, because you can't walk backwards.
It is able to walk backwards, because that's why we also have that -1. So if the first point is like depending how you draw it, if the coordinates are lower, if the first point is higher than the first point, it will be able to go down.
Oh, what I meant is it can't go change direction at some point or do anything like that.
Oh, no.
That's kind of what I meant.
From one point to another, and that's it.
Exactly. Still a very efficient solution, I think, this, because could this logic be applicable to 3D space? We have a question there. Potentially, but only for equally simple lines, I suppose.
Unless we need to change that iterator function to actually do a proper line interpolation between 2 points.
Yeah.
And then I suppose we'll need to decide also. Yeah, I think there are like quantization function. I don't want to say something stupid because I'm not an expert in this field. But of course, you need to approximate how do you draw a line in a pixel space, so a discrete space. So you'll need to figure out exactly how to approximate lines that are in an angle that is between 0 and 45 or 45 and 90.
Yeah.
Because there you'll need to take some approximation.
Yeah, the way it is now, I guess you could add a third incrementable position to it, but it would have to be lines that are 90 degrees or 0 or 180 or something like that in either one of the planes that you choose to look at it, or 45 degrees in all of the planes that you look at. So it will, like, you could run it against a cube, for instance. It could go from one edge of the cube down to the other edge of the cube, but it wouldn't be able to go in between, or it could go down one side of the cube, if that makes sense.
Yeah, because we are only incrementing by 1 or decrementing by 1 in every coordinate. So that's the kind of movements you can do, either straight or perfectly diagonal.
It could be 3D, though, in that way. And this reminds me of the fictional 4-dimensional space exercise from 2020's challenge. Yeah. I don't remember. I think it was a Game of Life type thing, that one. Yeah, we had to simulate, cells. Yeah, we called them cells, I think, in a 4-dimensional space after being 3D, yeah. It was somewhat similar to this because we had to calculate neighbors. It wasn't going in a line, but it was more finding what's next to you.
And in that one, we also used this concept of a sparse space where we didn't know the actual size because it was always expanding. We only knew points in a relative space. So rather than trying to pre-allocate the entire grid, we used like an hash map or a B3, I don't remember, to keep an association between point that existed and a value. Actually, there we maybe just use an hash set because
I think it was a
no
hash
association.
Yeah, I think it was just a hash set of points because the points themselves represented something. And they had the X, Y, Z, and I forget what we call the fourth axis. But yeah, it was interestingly similar to this in many ways.
Okay, so what
we should have put a link to it.
we can probably add it in the description on YouTube, so you can probably check that out if you want to compare the two solutions.
Yeah.
Quick thing. Should we try to improve this a little bit, or do we want to try to go to the next one?
Well, we did get a suggestion for that single match. I'd be curious to hear more about it.
Yeah, I'm also curious to try. So if I understand correctly, we could create a tuple that compares this one and this one in one go. And then we could have all the possible combination of matching.
Yeah, that's what I imagine as well, with like true, false, or whatever, greater,
So
less,
I'm
less
gonna
greater.
try to do it. So increment x and increment. By the way, meanwhile, Tommaso, feel free to tell me if this is not what you meant. So here what we want to do is a match where we are trying to match x2 CMP reference to x1 and then y2 CMP reference y1. Is that it?
Maybe.
Let's see. Well, here what can happen is that you can have greater and greater, I guess, is the first case. And in this case, we need to return 1, 1.
Yep.
Then we can have greater
and less.
By the way, we can also import ordering here so that it's less verbose.
In this case,
maybe let's do that. Use ordering.
Match can return a point and implements plus between point. Okay. So you're okay. So Tommaso was suggesting then that instead of us using two separate variables for increment on x and increment on y, we could return a point that we could add to an existing point. And that could be like a point that has 1, 0, or 1, 1, or 1 minus 1, and so on. But we still have to deal with all the combinations of greater, 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 less, greater, equal, less, greater, less, 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 equal, and so on and so forth. So it would turn into 9 lines, I guess, because we need to handle all combinations.
I think so, right? Because this is greater and equal.
Yep.
So this will be 0. And of course, here we could return a point straight away, right?
Yeah. Just keep it simple for now, I guess.
We have greater on one side and less on the other.
Yep.
So this will be -1 and 1.
Then
less and less. Then we have less and equal, so -1 and 0. And now we have all the equal.
Yep.
Equal and greater. So this will be 0 and 1. Then 0 and -1, which is less.
Yep. And then we'll have equal, equal, which is the last case. 0, 0, yeah.
0, 0.
Even if it returns point, I think I prefer... Actually, I think I prefer our original implementation because a point isn't used as a modifier for other points. They're just kind of kept as references to a spot on our space. Also, it's less code, as in I find the first approach easier to read.
I would personally agree. I can see the advantage here in returning a point. But at the same time, we will need to either implement the addition between points, which is something else we can do, and we have done somewhere in some other exercise, I think. Otherwise, I mean, it could be slightly less verbose when you use it, but here, because we only have 2 coordinates and we do additions just in one place, I don't know, it feels a little bit of over-engineering.
Yeah. Well, it's a good approach to keep in mind for future use that we can, and technically we knew this, you can do a match of multiple comparisons or multiple conditionals, if you will. Things. Multiple callable things.
And the cool thing is that if, for instance, we forget to do this, Rust's going to complain. It's going to say you are not matching exhaustively this pattern. So this is actually convenient that if you're really doing complex matches.
Does it not give us the same complaint if we miss one of the ones on top?
Oh yeah, of course. Yeah, if you remove one, it will complain as well. But I suppose here it's easier to cover all the cases if you have something a little bit more complicated because here it's actually smart enough to look at all the possible combination between all the cases here and all the cases here.
Yeah.
So it's actually pretty impressive for me that it's able to cover all the stuff.
Yeah.
Here is a little bit more straightforward because it's just looking at one enum and figuring out if you're covering all the variants. But here is actually multiplying all the variants of two different enums.
Yeah, fair enough.
So let's remove all this one. And I do like that, by the way, we did this use ordering, which makes the code a little bit more concise. Like we don't need to repeat ordering, and so on.
Yep, that is nice.
The other thing that I wanted to do, because this is something we were struggling with in the last session, is trying to generalize these two functions. So for instance, by doing a function that gives you an iterator over segments from the input. And it's something we tried to do in the last episode, and we did fail a little bit. And then offline, we went off and we really figured out what we did wrong. So hopefully now we should be able to do it. Let's see.
Theory, yeah.
In theory, yeah. So what we want to do is get segments, let's call it, or make segments. I don't know.
Sparse segments, technically.
Or just segments from input.
Segments, yes.
And what we want to do is this function will take an input as a string, and it returns, and this is where we failed, but we can just say imp iterator where item equal to segment. And I think that should do it if my memory is okay.
Don't we have to deal with lifetimes a little?
We might.
I think we did.
I think we might have to say plus this to make it
happy.
Let's see, why is it complaining? Because we are not returning yet? Okay, let's copy paste this because this is literally what we need to return without the filter.
Yeah, and you can remove you're not returning yet, you're just defining it.
You're right.
You can remove the definition and that should...
Okay, so now it's happy. Let's see if we really need this one. We do, yeah. I suspect, I'm not really sure about why. I suspect because this has an implicit lifetime. So this is saying kind of infer and respect the lifetime of this one.
Yep.
Please let me know in the chat if you know any better, because maybe this is the most stupid definition ever or explanation ever.
Not super sure I got how that works either, but okay, so we can make use of it here now.
So at this point, what we can do is segment input, and that will do it. And the same here, we actually removed a bunch of duplication, right?
Yep.
Segments input. Actually, this is shadowing a little bit the function, which is a little bit crappy, but whatever. Maybe we can rename this to, I don't know, segments either.
Yeah.
Okay, so now another thing that we could do is another function that is count intersections, which takes an iterator, right?
No, it takes a space.
It can create a space. We only wanted to return the intersection. So u sides, right?
Yeah.
But we need to take
we
segments, which is implement iterator item probably we don't even need this one at that point, do we? Okay.
Oh, yeah, okay, I see what you mean. So you want to create the space inside this function.
Exactly, yeah. So this is, of course, eager because it's going to allocate and do stuff.
Mm-hmm.
But at the end, we just need to count. Like, we don't really need to keep the space around.
Mm-hmm.
So I think we can literally copy all this stuff here. Actually, no. Let's copy this one because the name then is the same.
Yep.
And that seems to be fine. So at this point, let's do this one first because it's easier. Like at this point, we can just return count intersection segments.
Perfect.
Let's see if this still works. Seems fine. And now here is where it's interesting because let's do it from scratch. Actually, I just want to keep this filter.
Yeah.
But basically what we can do is I'm curious if we need to, probably we can just do count intersections of segments iter input, and then we put the filter here.
Yeah, probably.
Is that going to work? And the same we can probably do here.
Yeah.
We could just do this.
See if the tests run. If the tests pass, sorry.
But does that make sense?
Yeah, it does. It does.
Okay.
After filter,
everything is still working.
Like after filter, it should still be uniterable, so this should be fine.
Yeah, so that's actually the beauty of iterators in Rust, because they are very composable, being lazy.
Yeah.
Cool.
Yeah,
I don't have any other idea for improvements, so I'm probably just gonna commit this.
Yep, definitely commit, push. We can merge after.
Give me a terminal. How did you do that?
Like that. I don't know. I haven't yet learned how to use this editor.
So small improvements. Do we think it makes sense to start explore the other one, or we want to finish the stream a little bit earlier?
Usually we stay for around an hour, but I don't think 15 minutes is enough to go through the like. Probability is the next one isn't going to be as simple and quick as this one, so we're probably going to get started and have to end it halfway or something. But this is just a wild guess, so...
Yeah, let's finish the stream here for today then, and
fair enough.
We'll continue next Monday with the other ones.
Okay, so we'll wrap it up here then. You can find the recording on YouTube for this. The link is in the on Twitch in the About section. If you're watching this on YouTube, we live stream this every Monday at 6 p.m. Irish time, Dublin time. You should find the link to Twitch in the description on YouTube and vice versa. Sorry. So make sure to check out both of these things. Make sure you follow us as well if you find this cool and you want to be notified of when we release new stuff. Feel free to leave us comments and open PRs, by the way. The code is on GitHub, like we said before. So any sort of improvements or comments or anything is greatly appreciated. We are trying to learn, so don't expect our solutions to be the best or the most idiomatic. So yeah, if you know any better way of doing this, do let us know. Thank you for the suggestions and collaboration. We got some cool stuff today. And I think we're going to raid someone as well, right?
Yes, and it's somebody that is streaming a lot of cool Rust stuff, so way cooler than what we generally do. So hopefully you will enjoy that.
Nice. Have fun.
Bye, everyone.
Bye. See you.